Okay, so now continuing to go through section 2.1, thinking about the Bernoulli distribution as an example. So our outcomes are 0, 1s. Just as a reminder, the link to this paper and the complete playlist that I'm making on this paper are in the description of this video. So in the previous video that I made, I talked about how the Bernoulli distribution can be written as part of the exponential family distribution, right? So this is the exponential family, this is the Bernoulli, and we showed that you can write this Bernoulli distribution like this as long as you identify these guys as your variables or as your functions. Okay, so theta, or alpha of theta, which I think I might have neglected to point this out, but it's 1, right? Because you would need 1 there. So in the previous video, I might have forgotten to point that out, but it's not a huge deal, because really the big deal is what is theta, okay? And we identified this in the previous video, and then also what is g of theta, and we showed this in the previous video. Okay, so now we're going to have to use these to find what those weight and that modified variable y is going to be. Okay, and then we can basically construct an algorithm to estimate our betas. All right, so before we get too far, just remember. So we've identified the outcome variable z, right? We also have y. Okay, so y sub k equals the sum of these independent variables times beta. So those x's times beta. Okay, so beta is what we're trying to estimate. All right, so remember in GLM you have a random component, and then you have this component over here that's not random, and then you have to tie the two components together using your link function. And the canonical link, means lots of different choices for link functions. The canonical link function sets theta k equal to y k. All right, so here's theta k, and then you would set it equal to y k. So in other words, our yk would just then equal log of pk 1 minus pk. All right. It's often also called the logistic link function. All right. So now, using this link function, we can find what our weights are going to be. So let me scroll down here. So the weights equal derivative of mu d capital Y, all right, squared divided by vk. So we need to start with what is mu. Mu is the expected value of z, which is the same thing as the first derivative of the function g, right? If you're like, well, wait a second, where'd that come from? That was it earlier in the paper. We showed that. Okay, so earlier in the playlist, we showed this relationship right here. Mu is the expected value of z, which is the first derivative of g. Okay, so now we can use that because we know what g is. So let's go ahead and plug that in. So this is going to be d theta k, and then g is the log of 1 plus e to the power of theta k. Okay, so now I just need to use my properties of how to take derivative of a log. So it would be 1 over what's inside here. Oops. All right, times the derivative of the inside. Right, so it's like chain rule. Okay. All right, so that's what mu is. If I want to write mu with regards to with regards to y, remember that theta is y. So I could write this with regards to y, because I want to take the derivative with regards to y. Theta is y, according to the canonical link. All right. All right, so now I can find the derivative with regards to y. All right, so now I just need to use my rule for how to find the derivative of a quotient, right? So I'll take the bottom times the derivative of the top, which will just be itself, minus the top times the derivative of the bottom, which the 1 will cancel, so I'll just get e to the power of yk, all divided by the bottom squared. Okay, now this can be simplified a little bit. I see basically I have this guy squared twice. So, oh, you know what? I think when I wrote the bottom, I should have put parentheses around that. So I need to go ahead and first distribute that. So let's go ahead and do this. So I'll have e to the yk plus e to the yk squared minus e to the yk squared. Okay, then the bottom squared. So now I see these guys cancel each other. All right, and so what am I left with? I have e to the yk 1 plus e to the yk squared. All right, this is d mu k divided by dyk. All right, so there you go. I'm halfway there, right? Because this formula has this squared and then divided by v. So I just need to figure out what v is. All right, so vk equals the second derivative of theta k. Okay, so if you're like, where did I get that from? If we go back to our paper, we found it right here. All right, and we notice, so this is basically going to be the derivative with regards to theta of the first derivative. So we already found the first derivative. Let's go back up. Right, we found the first derivative right here. Then we found the second derivative basically, but we replaced the y's with k's, right? But we basically found the second derivative when we took the derivative again right here. So what is v? V is going to be exactly equal to the first derivative of mu with regards to y. Okay, so that's kind of nice. That leads to a nice cancellation. Basically, this v will cancel with one of these. And in this scenario, this is going to equal, the weights are just basically that, that first derivative, right? Because if it's squared, and then v is just the same thing. So you see how it cancels. So you're left with just that first derivative right there. Okay? So then, if I go back to my paper, so we have y, z minus mu. We've already identified what mu is, and we've already identified what d mu dy is. So now I'm basically, I have all the parts I need, right? Basically what I needed was just what's mu. Like, this is what's most important here. What's mu? and what is d mu dy. I can use these parts, these pieces here, and then plug them in, and then I'll have an algorithm where I can estimate what beta is. Okay, and that's what I want to do next. I'm going to do that in the computer program R, and we can see how this comes together, how this works.